All right, so we're going to be working with some applications of exponential functions and logarithmic functions. So here we have this question that there are 95 mice and the population increases by 30%. What's the new population of mice? So how many mice are there now? Well, we start off with 95 and then we're going to add 30% of 95. To get 30%, we just multiply the value by 0.3. So 95 times 0.3 is going to be 28.5. So if we add these together, we're going to get 123.5. Now how can we have a 0.5? Well, we're always going to round up. So even if we had a 0.1, we're going to round because we're not going to have half of a mouse running around. So we're going to say this is 124 mice. That was nice, right? Just find 30%. And if you shop, you go to a store and there's a jacket that's 30% off. Maybe you do a little math like this on your phone calculator and you can calculate the new price. That's simple. But what about if we ask for the population of the mice after 3 weeks? What about after 20 weeks? After 100 weeks? Are you going to do this process the same time? Because remember, 30% of 95 is only after the first week. Then after the second week, you're going to take 30% of this new value. So the percentage changes with each week, which makes it a little bit more difficult, doesn't it? Well, let's start off with 1 week, right? We had the population, and that was equal to 95 times plus 1.3 times 95. Now, where do I get this 1.3 from? Well, because it's an increase of 30%. So if this were 100%, that's what we start with. We have a 30% increase. So now there are 130% of mice, and that's 1.3. Well, if I factor out that 95, I get population is going to be the original value, plus how much did we add? We added 30% of the 95. I'm getting ahead of myself, sorry. So we added the 35, and that's how we got our answer. Well, what if I factor out that 95? I get 1 plus 0.3. And so this would be a 1.3. That's where I get that 1.3 from. If we do 95 times 1.3, we're going to get that 123.5. We're going to have that 124 mice. This part right here, this is what changes each week. So if this is going to be how many weeks it is, we can add a variable in here. This is our exponent. This t is going to stand for how many weeks afterwards. So how many mice do we have after the third week? Well, this is going to be 95 times 1 plus 0.3 to the third. So if I do 1.3 to the third, that's going to be 2.197. So what is that times 95? That's 208.715. And again, because we want whole numbers for mice, we're going to say 209 mice. So after the third week, we're going to have 209 mice. After the first week, we had 124 mice. So we have this steady increase of 30%. We're adding 30% each week. And so that's what we have here, and that's all that's going on. So this is an exponential growth problem. So I can move move all of this around. So this is exponential growth. Now you might see the formula written in a bunch of different ways. Exponential growth. But the new value is going to be equal to the original value times 1 plus the rate to the t. So this is going to be your original value. This is your rate. Here we have a rate of 30%. So we always want to write that as a decimal. And then t is time, so after how many weeks? Now if it's a decrease, the only thing that's going to change is this. So if we have population decreases each week, this would be a minus r because it's a negative rate. But everything else is just going to stick with this. Now, one of the most popular applications is compound interest, which you may have seen before. So this, if we have compound interest, here I'm going to write this as A for account is equal to P for principal. That's your initial investment plus R over N to the NT. So here P is principal. Helps if I spell it correctly. Principal, so it's the initial amount. R is the rate, again, as a decimal. N is the compoundings, so how often. And T is time. So when we say compoundings, it's how often you are paid. Most checking and savings accounts that I've seen will do a monthly compounding, meaning at the end of every month, they take how much money is in your account and they pay you a percent. So after a certain amount of time, you will grow a whole lot of money. Actually, Ben Franklin, who hopefully you know, he was one of the founding fathers, he was from Boston, but he's moved to Philadelphia. He's big with Philadelphia and the Revolution and all that stuff. What he actually did was he left in his will money to Philadelphia and Boston. However, they were not allowed to open up those accounts to touch that money until sometime in the 20th century, maybe in the 1980s. So what those cities did was they invested it. They just stored it. And so banks paid interest. And so 30% of, for example, of the mice population, from our previous example, 30% of 124, 30% of 95 got us to 124. Then we take 30% of 124. Well, that's going to be larger. And so when you're taking in a larger amount, a larger percentage each time, that money grows. And so by the 20th century, when the cities of Philadelphia and Boston could have that amount, they actually had, we're talking millions of dollars. So if you want to be rich, all you got to do is just invest like $200 and wait a couple hundred years. Now, here's what our examples are going to look like. So here we have $7,300, which is going to be, we're going to gain interest on at 7%, and it's going to be compounded semi-annually. God, I hate semi-annually. Why don't we change some of these around? That's going to be monthly. We'll say this is weekly. All right, semi-annually. I don't know, maybe it's biannually. We're going to say it's 2 times a year. So this is 2 times for each year. So each year, 2 times. So if we look at that formula, we're going to have A for account balance, right? A is equal to P times 1 plus R over N to the NT power. So we're looking for A, we're looking for the account balance. P is going to be the principal amount. So how much should we start with? 7,300. We multiply that by 1 plus the rate. Now the rate is 7%, so that's going to be 0.7. 0.07. It's a 7 in there. Really having a hard time. There we go. Over n. N is going to be how many times we compound per year, which is 2. Raised to the n times t. Well, how long are we waiting for this? 3 years. So all you want to do now is just put this into your calculator. So 1 plus 0.7 and so when we do this, we're going to have 7,300 times 1 plus 0.07 divided by 2 to the 6th power. And so after 3 years, with doing nothing, we're going to get 8,973 and 56 cents. Now the decimal actually goes on longer, but whenever we're talking about money, we just want to have 2 decimals. So always round this appropriately. But that's it. For this next one, we're compounding monthly, so that's going to be 12. So again, we use that same formula, P times 1 plus R over N to the NT. So the principal is 1030, 1 plus the rate, which is 0.04, over the N, which is 12, to the 2 times 12. Or maybe I could rewrite that as 12 times 2, so I don't confuse anybody. 12 times 2. 2 for 2 years, because that's what we're looking at after how long. So here we're going to do the same amount. So this is starting with $1,030. The rate this time is going to be 4%. We're going to divide this by 12, and we are going to raise this to the 12 times 2, which is 24. And that should give us not a whole lot. After 2 years, we haven't made a whole lot. It's just going to be $1,115.64. For 13, we again write that formula. Account balance is going to be 18,000 times 1 plus the rate, which is 0.09, over n. How many weeks are there in a year? 52. So if we're looking at weekly, it's 52. So at 52 times 6, so this is going to give us 18,000 times 1 plus 0.09 divided by 52, all to the 52 times 6 power, whatever that is. And so this is actually going to be a hefty amount here. So this is 30,873.71. So after 6 years, we've we've almost doubled our initial investment just in compounding at 9%. So that's pretty good. Very rare though, very rare. You won't see savings accounts like that. All right, here we have another one. And this time we're just investing annually. So N is how many times per year. So annually means once per year. So the rate is 0.07, and N is just 1. So we're going to have the account balance is going to be 1,500 times 1 plus 0.07 divided by 1, which is just 0.07, to the third. And so here is 18.37 This is dollars. Okay, so file this formula, plug it in. A lot of times people get confused with compoundings and time. Time, you should always see years, how long you're looking for. The compoundings is how often. So it's usually with this word compounding or compounded. Now sometimes we're continuously compounding. So every second, every nanosecond, we are just continuously compounding. The formula there is principal times the natural base, which is e, to the RT. So all of our variables are the same. This is the natural base, which your calculator actually has a button for. So if we look at pretty much those same questions again, we're going to be using this same formula again, this a-pert formula. So we can just copy that for each one of these. It'd be great if you guys could do that in your notebooks, right? And okay. And plug in our values. So A is equal to 7,300 e to the 0.07 times 3. So the only thing we drop is that compounding, that n value. So 7,300 e to the 0.07 times 3, that's going to give us an account balance for $9,005.85. So we can compare that with what we had before. So it's a little bit more. Not a whole lot, but a little bit more. The account balance here will be 1030 e to the 0.04 times 2. So the account balance is going to be 1030 e to the 0.04 times 2. And this is going to be $1,015.79. So actually, that's pretty close to what we had before. We made just a few more pennies on this. So the compounding doesn't always make it a whole lot more, but it should generally be increased. Now here, before we had these same values, and we almost doubled this amount. So now we're compounding continuously. So let's see what we get this time. We get 30,888.12. What do we have before? How much do we have before? Those same values. 873. So we only made $12 more, or however many more dollars. 15. So not a whole lot more, but it's still more. Oops. So here we want to plug these values in. So we're going to have 1500 e to the 0.07 times 3. So the account balance is 1500 e to the 0.07 times 3. So this is going to be 1850.52. That is our final answer there, 1850. So we made a little bit more. So you can see that when we compound continuously, we're going to make a little bit more. All right, so a lot to do here, but understand these formulas. So we have the continuous compound interest when we don't have any compoundings. When we say that we compound continuously, that just gets rid of the n, and we make the base of the exponent in e. We have the original compound interest formula, which really does follow the exponential growth formula that we initially looked at. So we're going to be looking at some applications of these, some other word problems, which I know you all love. So just make sure you get in practice with this, and let me know if you have questions.